All right. I'd like to introduce our next speaker, Dennis Eichhorn, coming to us from UC Irvine. You're on, Dennis.
Thank you. Everything I talk about today is going to be joint work with Shane Chern, Shishuo Fu, and James Sellers. And I'm going to talk about the combinatorics of sequences that enjoy a curious self-convolutive property. I'll start out by defining partitions with designated summands, which were the objects that kind of launched all of this research. That will lead me to define a new concept called two-convolutivity. I will spend most of the rest of the talk talking about two-convolutivity, but then at the very end, I'll also include some interesting constructions, generalizations, and some open problems. So in 2002, Andrews, Lewis, and Lovejoy defined partitions with designated summands to be partitions where exactly one part of each side is designated or marked. So for example, here is a partition of designated summands of 13. There is a 5 that is designated because one part of every size must be designated. There are 3 2s, and the second 2 is designated. We can only designate one part, and we must designate one part of size 2. And then we have 2 1s, and the first one is designated. So that is a partition with designated summands, and of course we count them. They also studied partitions into designated summands, all of whose parts are odd. And I'll refer to those as PDO partitions. Below we see as an example, there are 8 PDO partitions of 5. There's a designated 5. The partition 3 plus 1 plus 1 occurs twice because there's 2 different ways to designate the ones. And then the partition that is the sum of 5 ones occurs 5 times because, well, 1 time for each one that can be designated. So PDO of 5 is 8. Now, PDO is actually pretty interesting. Andrews, Lewis, and Lovejoy found a recurrence. They were able to completely characterize its parity. It has connections to generalized Frobenius partitions. It has divisibility mod 3 in arithmetic progressions. Sellers wrote a paper where he gave infinite families of congruences modulo powers of 2 for PDO. Chern and Sellers wrote a paper where they gave an infinite family of internal congruences modulo powers of 2 for PDO. And even in the original paper, Andrews, Lewis, and Lovejoy gave a generating function, and they also gave some interesting dissections of that generating function. We're going to look at the first one right now. So throughout this talk, F is very important. F sub j is this infinite product. If you like Pockhammer symbols, this is q to the j semicolon q to the j sub infinity. If you like modular forms, this is essentially eta of jz. But they found that the generating function for PDO was this F quotient right here. Now, this was on page 2 of their paper. On page 15 of their paper, they wrote down the following dissection. If we just look at the generating function for PDO of 2n, we get this F quotient. If we look at the sum of PDO 2n plus 1 times q to the n, we get this F quotient. Now, if you look at these 3 F quotients carefully, you're going to see something very curious happens. The first part of the 2 dissection is exactly the square of the original generating function itself. This is a very curious property. When I first heard about this in 2024, I had never seen this phenomenon occur anywhere else in anything I had studied. But it happens here. So we now define any generating function or sequence that has this property as being two-convolutive. So if the first part of the 2 dissection is exactly the square of the original generating function, we say the generating function is two-convolutive. And equivalently, if the odd index terms of the sequence just come from the convolution of the sequence with itself, we say that the sequence is two-convolutive. We'll say both the sequence and the generating function are two-convolutive. 13 years later, Barua and Oja pointed out that, well, 13 pages apart in this paper of Andrews, Lewis, and Lovejoy, sure enough, PDO is two-convolutive. Now, the term two-convolutive didn't exist at that point, but they observed this, and they explicitly mentioned boy, it would be interesting to find a combinatorial proof. And I wholeheartedly agree. So what would a combinatorial proof of two convolutivity look like? Well, if this convolution identity holds, it means there should be a bijection between PDO partitions of 2n and pairs of PDO partitions with total weight n. That's what a combinatorial proof should look like. A bijection between PDO partitions of 2n and pairs of partitions of PDO partitions of combined weight n. So this is the bijection we're looking for. So of course the question is, well, what is this bijection? I first heard about this open problem in a talk by James Sellers at the George Andrews Bruce Barrett Birthday Conference 2 years ago in 2024. And, of course, Brew and Oja didn't have a bijection. Sellers wrote a paper about this, no bijection. Chern and Sellers wrote a paper, no bijection. Then, eventually, Fu and Sellers wrote a paper together where they actually give a two-parameter refinement of the identity that witnesses the two-convolutivity of PDO, but they couldn't come up with a bijection either. Well, undaunted by all this, I heard about this in summer of 2024. I thought, I'm going to come up with this bijection. So I thought and I thought and I thought for about 6 months, and I absolutely could not come up with a bijection. I couldn't come up with anything close, but I knew what to do. I decided I would call for help. So I assembled, called up Shane Chern and Shisho Fu and James Sellers and said, I'll tell you what, let's work on this and come up with this bijection. If anyone should be able to do it, maybe the four of us are likely candidates to be able to figure out this bijection. So at the time, we were in 4 different time zones. We Zoomed at all sorts of crazy hours. We constructed an overleaf, and we worked on this starting in December of 2024. So we worked on this, and after working on this for almost a year and a half, I can announce that, well, as of 2 months ago, we still just didn't know. We just couldn't come up with this bijection. It's a very tricky question, but we didn't give up there. We didn't give up just because we couldn't find a bijection. We thought, well, maybe there are other two convolutive sequences. And if there are, maybe if we can figure out something with those other two convolutive sequences, it'll shed some light on PDO. So we searched. We searched the online encyclopedia of integer sequences. This is the natural thing to do. Of course, when you're looking for interesting sequences, search the OEIS. Now, you may not know, but you can actually download the whole OEIS yourself. So we did that. And then we just went through all of the sequences in the OEIS and checked to see, are the even index terms of the sequence at the very beginning of the sequence coming from the convolution of the sequence with itself? Well, we went through the whole OEIS and did this. We excluded some trivial solutions and dilations. And we found that out of over 385,000 sequences, only 6 of them were even potentially two convolutive. So in this sense, two convolutivity is very, very rare. Here are those 6. One of them, of course, is PDO. That was already in the OEIS. Notice that 5 of them are these F quotients. And then there's one kind of outlier, which I will say very little about until the very end of the talk. So there's all these F quotients that are two convolutive, or at least candidates to be two convolutive. So we set about trying to prove whether or not they were actually two convolutive or not. And sure enough, they all are. Now, the two convolutivity of PDO already follows from what Andrews, Lewis, and Lovejoy did in 2002. It's already in the paper. The facts are kind of 13 pages apart, but it's already in there. And we were able to prove, using Q-series techniques, that all 6 of these are actually truly two convolutive. But of course, the question is, we want to find combinatorial proofs. So you can ask, are there combinatorial proofs of the two convolutivity of any of these 6 sequences? And the answer, thankfully, is yes. So we finally had a positive result in May of 2025, about 14 months ago. We were able to give bijective proofs of the two convolutivity of these 3 generating functions here in red. How did we do this? Well, we started by giving a combinatorial interpretation of each of those three generating functions. It turns out you can combinatorially interpret each of those three in terms of partitions. Then we wrote down the description of the set X of partitions that that generating function generates. And then we were able, in each of those three cases, to construct a weight halving bijection from the elements of X of weight 2n to pairs of elements of X of total weight n. We were able to do this just using a few ingredients. We needed 4 relatively simple bijective lemmas, some of them classical, some of them new, but very straightforward. And then we also needed a slightly more complicated bijective version of Jacobi's triple product identity. And with those ingredients, we were able to cook up bijections for those 3 generating functions. But now there's still 3 left here in this list from the OEIS. And we convinced ourselves after thinking at great length that the same technique just doesn't apply. We can't apply that technique, so we had these 3 other generating functions that we proved are too convolutive. We proved analytically that they are too convolutive, but we couldn't come up with bijective proofs. So we just needed some new ingredients. This was in May of 2025, but we just had no idea what those new ingredients would be. So we kind of put this on the back burner and started thinking about some generalizations. We started thinking about something we called odd to convolutive. And in thinking about odd to convolutive things and searching the literature, we were led to a very interesting paper by Farkas and Kra, which some of you may know about just when I mentioned their names. And then we remembered, well, this stuff of Farkas and Kra was treated combinatorially by Ole Varnar and Sun Kim. And in looking at those papers, we found a super delicious ingredient, and that is this partition identity of Sun Kim that was proven bijectively. So this ingredient is actually a bijectively proven partition identity, where the partition identity is between partitions of 2n into distinct parts, where the parts come from a certain family of odd residue classes, mod 2m. And the second partition function is a number of partitions of 2n into distinct parts, where the parts come from a certain collection of even residue classes, mod 2n. So as it turns out, this ingredient was exactly what we needed. As of 2 months ago, we still didn't have that bijection, but finally, I can announce that we do now have a bijective proof of the 2 convolutivity of PDO as of less than 2 months ago. So let me introduce some notation and give you some indication of the proof. Let P be the set of ordinary partitions, O the set of partitions into odd parts, D into distinct parts, D0 into distinct parts, but there could be a part of size 0. Let DMA be the set of partitions into distinct parts congruent to A mod M, DM plus or minus A into distinct parts congruent to plus or minus A mod M. Script PDO is just the set of PDO partitions, and T is the set of triangular numbers. I'm saying set in quotes because the 4th triangular number is 6, and the minus 3rd triangular number is 6, but I'm going to treat those as different instead of as the same. Okay, so with this notation and a couple more pieces, if I say square brackets even, that just means look at the even-sized elements inside the square brackets. And if I take a constant multiplied by a set of partitions, that just means multiply every part in every partition by that constant. Okay, with those notations, we can now write Sun Kim's bijectively proven theorem in the following way. If alpha, beta, and gamma are odd, then the even-sized elements in this quadruple of sets of partitions, where the partitions are in distinct parts and all of them are in one of these odd residue classes, those are in a weight-preserving bijection with partitions in this quadruple of sets of partitions, where all of these parts are in even residue classes, mod 2n. Okay, so there is this weight-preserving bijection. That's what Sun Kim showed. And like I said, this is the key ingredient we need. Um, but you might be asking yourself the question, what does this have to do with PDO? None of this looks like PDO. Well, as it turns out, we can bijectively rephrase PDO in the language of partitions into distinct parts. We were able to come up with a weight-preserving bijection from PDO to some three-colored partitions, namely the set of three-colored partitions where the blue parts are distinct, orange parts are even and distinct, green parts are distinct odd multiples of 3. In other words, we have a weight-preserving bijection from the set PDO to the set blue D cross orange 2D cross 3D21. D21 is just partitions into distinct odd parts. I'll sometimes say D odd instead of D21. But we came up with a weight-preserving bijection here. I'm not going to go into complete detail of how we did it, but I will say it comes in two pieces. We first gave a bijection from PDO to O cross 2O cross 3D odd. And then Glacier classically gave us a bijection from O to D. So if we use that twice, we end up with a weight-preserving bijection here from PDO to D cross 2D cross 3D odd. So we did come up with a bijection. It's relatively straightforward. We didn't come up with it immediately, but once we figured it out, it wasn't that hard. So now finally we can give a weight-halving bijection from the even elements of PDO to PDO cross PDO, and therefore bijectively witness the two-convolutivity of PDO. How does it go? Well, by our lemma, we have this weight-preserving bijection from PDO to D cross 2D cross 3D odd, so it suffices to show that there's a weight-halving bijection from the even elements in D cross 2D cross 3D odd to pairs of elements in D cross 2D cross 3D odd. That's what we need to show, a weight-halving bijection from here to here. So let's consider the even size elements in D cross 2D cross 3D odd, and let's separate all the parts in all those sets of partitions according to the residue modulo 12. So colors are preserved here. If we have a blue partition into distinct parts, of course, the parts have to be plus or minus 1 mod 12, or plus or minus 2 mod 12, or plus or minus 3 mod 12, etc. If we have an orange partition into even distinct parts, of course, the parts have to be plus or minus 2 mod 12, or plus or minus 4 mod 12, etc. And if we have green partitions that are in 3D odd, well, all the parts have to be plus or minus 3 mod 12. So by separating out these partitions into the residue mod 12, we get that this is in bijection with this expression. And then we can just regroup these terms. Let's put all the odd terms in front and all of the even terms in back. But then once we regroup these terms, we see that this object in the first set of parentheses is exactly the shape of the things in Sun-Kim's bijective theorem. So rewriting that exact same expression here on the next page, we see that this expression in red can be subjected to Sun-Kim's bijection. It is exactly her bijection with alpha equal 1, beta equal 3, gamma equal 5, 2m equal to 12. And Sun-Kim's bijection says that this is in bijection with this. Now, so we don't have to treat Sun-Kim's bijection as a black box. I'm going to go into it a little bit. First, a combinatorial lemma. Wright gave a weight-preserving bijection from D0 cross D to P cross T. In other words, Wright showed that if you have a pair of partitions into distinct parts, the first one of which might have a part of size 0, those are in bijection with ordinary partitions coupled with triangles. Just very quickly, how does this bijection go? Well, if you have a blue partition into distinct parts, and you draw its Farrer's diagram, skew it over so that this first column becomes this first diagonal. You have a red partition into distinct parts, skew it over so that this first column becomes this first diagonal. Then we're going to glue these two skewed partitions together. How? We're going to reflect this second partition along the line y equals minus x. And then we're going to glue these partitions together so that the bottom row of this first skewed partition, intersects perpendicularly what was the bottom row of this skewed partition. So that's how we're going to glue them together. And then we just change the colors. What we find is after we glue these together, we're going to have an ordinary partition in black along with a triangle in green. So this is Wright's bijection, and Sun Kim is going to use this in her bijection. Let's see how. So again, these are the two things in our theorem that Sun Kim's bijection treats. And we're going to give this bijection of Sun Kim in the following way. First, when we have parts that are 1 mod 12, we're going to subtract 1 from them. When we have parts that are minus 1 mod 12, we're going to add 1 to them. When we have parts that are 3 mod 12, we'll subtract 3 from them. When we have parts that are minus 3 mod 12, we'll add 3 to them, and so on down the line. So once we get rid of all the 1s, 3s, and 5s, we're going to set them aside. We'll have some surplus or deficit of 1s, some surplus or deficit of 3s, but we're going to set that surplus, those surpluses or deficits aside. And what we now have is everything's divisible by 12. So if we divide everything by 12, this quadruple here is going to be a quadruple of copies of D0 cross D. And then we can apply Wright's bijection 4 times. Then is the key step. This is where Sun Kim is incredibly clever. She does something truly spectacular. Once we apply Wright's bijection 4 times, she scrambles just the triangles. Let me show you what I mean. So you can imagine that this is the result of applying Wright's bijection 4 times. And in each of these 4 instances, we have an ordinary partition with a triangle. Well, in her bijection, she scrambles just the triangles. These black partitions, these black ordinary partitions stay exactly the same, but these 4 triangles of size 6, 1, 1, and 1 have been scrambled and reassembled into 4 triangles of size 0, 3, 3, and 3. So this is the key element of her bijection. And once she does this, of course, we can use Wright's bijection in reverse. And now we'll have 4 different pairs of copies of D0 cross D. We can then reinflate everything by multiplying all the parts of those things by 12. And then, because of exactly the clever way in which Sun Kim scrambled those triangles, we can exactly take all of the surplus or deficits, 1s, 3s, and 5s we have, and put them back together onto these 4 copies of D0 cross D inflated by 12 to get exactly this quadruple of sets of partitions. So this is how her bijection goes. It's very creative and very interesting. Once we've done this bijection, we've done something amazing. We now have that everything inside the square brackets is comprised of even parts. So we can just cut each part in half. So this is the weight halving part of our bijection. Our original expression is now in weight halved bijection with this set of partitions. Now, if we just regroup these and reconstitute these, we find that this is exactly a D cross 2D cross 3D odd squared, which is what we wanted. So this is our proof. Finally, after a year and a half of collaboration, we finally have a proof that, a bijective proof that PDO is too convolutive. Of course, the first thing we did is we asked, can this apply to other generating functions? And the answer is yes. The same technique shows that A128 is too convolutive. That was one of the black ones from the list. And then we also were able to give repeated proofs, new bijective proofs of the two convolutive generating functions that we already had bijective proofs for. So now the state of the situation is we have bijective proofs of the 2 convolutivity of the 5 generating functions in red, but we still don't have one of this one in black. So I'm running a little low on time, so I'm going to skip the constructions and talk about some generalizations. Of course, so far in the talk, all I've been talking about is 2 convolutive sequences, What about three convolutive sequences? You can define three convolutive sequences in the analogous way, where every third term of the sequence comes from the threefold convolution of the sequence itself. And you can ask, are there three convoluted sequences? Well, in the OEIS, there are four. They're all F quotients, and we were able to give analytic proofs that, in fact, these four are three convolutive. The truth is, these come in dual pairs. In fact, originally, there was only three in the OEIS, but we added the fourth because it's the dual pair of the third. So again, we have proofs that these are three convolutive. We have no bijective proofs. And then, of course, you can define n convolutive in an analogous way. We can construct some n convolutive sequences, but we can't find any that are F quotients. Are there any that are F quotients for m equal 4, 5, 6, etc.? We don't know. We don't even have a conjecture, but there's none in the OEIS of any type. Okay, so finally, some recent breakthroughs. We have two more F quotients that are too convolutive. We have analytic proofs, but we don't have bijective proofs. We also were able to generate 12 more F quotients that are three convolutive. We have analytic proofs. We don't have bijective proofs for any of them. So I'll finally close in my last minus 1/2 minute. Here is the list of all known self-convolutive F quotients. There are 7 two-convolutive F quotients, and there are 7 pairs of three convolutive F quotients. Is it a coincidence that the 7 equals 7? We have no idea. So finally, some open problems. We'd love to discover more self-convolutive F quotients or show that there aren't any. We'd love 16 more combinatorial proofs. We have 5. We'd love 16 more. We'd love to construct an infinite family of 2 or 3 convoluted F quotients or prove that none exists. And we'd love to find an F quotient that is 4, 5, 6, or whatever convolutive, but we haven't found any yet. Finally, I will say, we'd love to determine if there's a pattern among the known 2 and 3 convolutive F quotients. As of 2 weeks ago, we had no idea. But as of about a week and a half ago, we might have some ideas, but I'm going to have to leave that for another talk and another time. So with that, I thank you.
Thank you very much, Dennis. Questions from the audience? All right, so our next talk starts in 2 minutes.
Good day. So can I tell